So we're starting with f of x equals 1 over x. We're finding f prime of x. Again, if we're looking for the derivative, that means use the limit as h approaches 0 of the difference quotient. And so your first step, when you plug into the difference quotient, we end up with these fractions within the fractions. Yes, it looks scary. Can you deal with it though? Yeah, I think you can. So go ahead and make that a single fraction on the top from here. So in order to make that a single fraction on the top, we're going to have to get a common denominator. In this case, the only way to get that is by multiplying the two denominators by each other. So I end up with two fractions, each with a denominator of x times x plus h. And if you multiplied that through to make it x squared plus xh, that's perfectly fine as well. But then once you've done that, go ahead and do the subtraction on the top. And when we do that subtraction, the x minus x, that becomes 0 and goes away. And then we do nothing minus h, so that's why we get a negative h. So we have negative h over that x times x plus h, all over h. Now this is the point where sometimes people end up getting confused. In order to be able to deal with this at this point, remember that fractions are like division. So I'm going to take the same limit, so it's still the limit as h approaches 0 here. But I'm now just going to write this a little bit differently to make it easier to see why we're doing what we're doing here. It's going to be negative h over x times the x plus h, because that hasn't changed. And it's the same as dividing, so that's dividing it by h. Now if I'm going to do a fraction divided by h, then I'm going to turn that h into h over 1. And how do I divide by a fraction? Yep, we multiply by the reciprocal. So then this is actually going to become the limit as h approaches 0 of the negative h over x times x plus h, and I'm just going to replace what I wrote there, times 1 over h. And notice when we do that and multiply those through, those h's are going to cancel each other out, and so that's going to go away and that's going to go away. And so we end up actually now dealing with the limit as h approaches 0 of a negative 1, because remember it was negative h, over x times x plus h. And now that I cancel that h out of the denominator, the original one that was in there, notice I can use direct substitution at this point. I can plug the 0 in for h to figure out what my limit is. So go ahead and do that. Alright, so when we end up actually working all this out then, we plug 0 in for h, so the bottom becomes x times x, which is just x squared. So we now know that f prime of x equals negative 1 over x squared, or a negative 1 over x squared if you preferred. You could have written the negative in front of the fraction just to make it look a little bit cleaner, a little bit prettier. So this problem was basically just kind of a chance to deal with how do we find the derivative of a different looking type of function. But it's not going to be our main focus of today. Our main focus today is actually going to be dealing with concepts of objects positioned in space, specifically position, displacement, velocity, acceleration, ideas like that. If you were taking physics, this is going to be familiar kind of information, but perhaps in a slightly new context. So let's take a look through this, and I want to establish the idea of what this is always talking about, because you're going to see this kind of number come up a lot, and I want you to really understand what it's talking about, what it really means. So objects falling on Earth accelerate at a rate of 32 feet per second squared. Now when you see feet per second squared, what that really means is feet per second per second. And we're going to see how that's actually going to make sense here in a moment. Now this is a constant number, so wherever you are on Earth, this is the acceleration due to gravity. Alright, so in our example here, the vertical face of El Capitan in Yosemite National Park is about 3,000 feet tall. A stone falls from the peak. And so how fast is it falling after 1 second? Well, this is where the acceleration can help us, because acceleration means that our velocity is going to be increasing. Our speed is increasing 32 feet per second. So this is the amount that it's increasing by every second. So that's what acceleration is really saying. It's how quickly is the speed increasing. So after 1 second, what would our speed be? 32 feet per second, yeah. After 2 seconds, how fast would it be falling? 64, yeah. 64 feet per second, because every second it goes 32 feet per second faster. And so after 3 seconds, how fast is it going? It is another 32, so basically 3 times the 32. So yes, it is 96 feet per second. And that's what acceleration is meaning, is basically acceleration tells us how quickly the speed is changing. And so with the same situation, it's the vertical face of El Capitan, we can now see this equation over here. H of t equals 3,000 minus 16t squared. Perhaps later on we'll get in and see exactly how we write that equation from scratch. But for now I'm telling you that's what the equation of the height of our object would be, the height of our stone that has fallen from the peak. So what we now want to do is we want to write the equation for the instantaneous velocity of this stone. Notice I'm even telling you how to find it here. The instantaneous velocity, that is velocity equals h prime of t. That is, take the derivative of h of t here. So please do that. Find the derivative of h of t. Alright, so in order to figure this out, we end up using our difference quotient like we normally would. And we go ahead and we simplify that through. We find the limit as h approaches 0. You should be finding now that v of t, which is just the derivative of h of t, equals a negative 32t. Now that we have our equation to find velocity, negative 32t. Same problem, but this time please use your equation for v of t that we just found to find the velocity of the stone after 3 seconds. Should be quick and easy to do that. So we're basically doing v of 3 here, which is going to be negative 32 times 3. And so when we do negative 32 times 3, we end up getting negative 96. And technically our units here are, not meters, feet per second. And I said to compare your answer back to question number 3 that we did. So that was the one where I just said, if it's falling at, or accelerating at 32 feet per second squared, after 3 seconds, what is it? And there we came up with an answer of 96 feet per second. It wasn't negative. This one's negative. And I just want to bring this up as one of those subtle details that we'll be able to get into more later, but I want you to be aware of now, is that the first one was just asking how fast is it going. Basically, that's asking for speed. Speed is just a description of how fast it is going. Velocity is slightly different. Velocity is how fast it's going in a specific direction. So velocity will consider whether it's going up, whether it's going down, or whatever it is in that particular situation. In other words, velocity has a direction to it, speed doesn't. So speed will always be a positive number. But velocity, it can be positive or negative, or 0, of course. New problem now. So we have a position in meters of a ball thrown upward, modeled by this particular equation here. What I'd like you to do is please find the velocity when t equals 2 seconds. And so, like that last problem, since you're starting with an equation that tells us a position, if I want to know velocity, I'm going to find the derivative of it. So basically what you're having to do here is figure out what f I'm sorry, S prime of t is, or more specifically in this case, S prime of 2. So in order to be able to figure this out, we're going to figure out what v of t is, and v of t is going to equal S prime of t. And so I end up finding the derivative function of 5 plus 30t minus 4.9t squared, and for that, after you did all the work, you should have found that it was 30 minus 9.8t. And then once you've done that, then you're going to go ahead and figure out what the v value is at 2. All right, now when you do that work, we go ahead and we plug 2 in for t, so we do 9.8 times 2, and then we subtract that from 30. You should be getting an answer here of about 10.4. Now this, remember, is talking about velocity, right? Well, we know what we're dealing with in this problem. We're talking about meters, we're talking about seconds, so please tell me that this velocity is measured in meters per second. So our final answer here, 10.4 meters per second is our velocity. And notice that since that's a positive number, that tells us that this thing is still traveling upward at this time. Then now a little bit more thought about what these situations really mean and what the derivatives can really mean in these. So we're not going to do calculations in this one, but we are going to be taking a look at, okay, what's going to make sense and what is it really telling us about what's happening here. So in this problem, the number of bacteria after t hours in a controlled laboratory experiment is found by doing n equals f of t. All right, and so the first question is, what is the meaning of the derivative f prime of 5? What would that actually mean in this context? Take a moment to think about that. Now there's a few different ways that you can look at this and understand what's happening. And I want to talk through a few of those different ones. Some of you you're going to look at and you're going to kind of know intuitively right away, but I want to be able to also give some tools for those of you who don't look at it and know right away. So like, what if we were making a graph of this? If we were making a graph in this situation, what would we label our x-axis here? It'd be time, which in this case is hours. So it'd be time in hours. So then what would our y-axis, our vertical axis, be labeled? Yeah, it'd be the number of bacteria. And what variable did they use to represent that here? N. Yeah. So N represented the number of bacteria. And so really, then it's asking, what is the meaning of the derivative? Derivative is always a rate of change. And more specifically, it's like slope of the tangent line. Slope, remember, we've seen it as delta y over delta x. What if I put that in terms of what I'm dealing with in this problem? Delta y is actually delta, that is the change in bacteria, over delta, that is the change in time, that is the number of hours. And so you could either write that as time or hours there. And so notice what f prime is telling us here. F prime is telling us how quickly the bacteria are changing over time. And so then the specific question that's being asked here, what is f prime of 5? This would be saying that after 5 what? Hours, yep, after 5 hours, how quickly the bacteria is changing, the number of bacteria. Now, thinking about this situation and what it's really talking about here, assuming in part B here there's an unlimited amount of space and nutrients for the bacteria, so we don't have to get into some of the biological nitty-gritty here, which do you think is larger here, f prime of 5 or f prime of 10? Well, again, we go back to thinking about what's it really represent, right? So it's how quickly the number of bacteria is growing over time. So what kind of shape of this graph would it be? I'm envisioning something that's looking like this, right? Because basically it's kind of like an exponential growth where like if it doubles after an hour, then we're doubling that doubled amount for the next hour after that, and then we're doubling that amount for the next hour, for instance. And so then, if I'm trying to figure out then, which do I think is larger, f prime of 5 or f prime of 10, where's the slope the steepest? At 5 or 10? 10. At 10. Yep. And so I would say that f prime of 10 should be the larger value, because it's where is it growing the quickest, or in other words, where is the slope the steepest for that problem. And here's a different example. This one's looking at volume, which is measured in decibels. So the volume of a speaker from d feet away can be represented as V equals f of d. So in this case, what is the meaning of f prime of 8? And again, take a moment to think about that. And like the last one, if you're having trouble conceptualizing what it's really talking about, a great way to think about it is, think about if you're making a graph, what would that graph look like? What would you be labeling on the axes as well? So like in this case, it is D on the horizontal axis and V on the vertical axis. And so if I'm thinking back to how the derivative is basically like a delta y over delta x, in this case that would mean delta v, let's write our v a little more cleanly, over delta d. So what's that meaning? It's the change in volume, because remember delta means change in volume as we have changes in that distance, that feet away. So basically, how quickly is the volume changing from 8 feet away in this particular example? All right, and then it's asking, is f prime of 8 going to be positive or negative? Think through that one as well. Would you expect the derivative to be positive or negative at 8? Now, if you're feeling stumped on this one, again, we can think about what the graph would look like. Let's say our volume started at some random value here. As distance away from the speaker increases, is our volume increasing or decreasing? It is decreasing, yes. Now, I'm not going to get into details about how curved it is there and which way the curve is going and all that, but it's decreasing from there. So is f prime of 8 positive or negative? It's negative, because remember it's representing the slope at 8. And it's decreasing, therefore our slope is negative. So the derivative then is negative as well. Last problem that we're going to be looking at for today, at least this and its follow-up. So in this case, we have a rock that is thrown upward. Notice there's lots of movement of objects in space here. On the planet Mars, because we get bored of using Earth all the time, with a velocity of 10 meters per second. We know its height in meters after t seconds is given by this equation, h equals 10t minus 1.86 t squared. What we're going to do is we are going to find the average velocity of this rock at 2 different time intervals. We're going to go from 1 to 1.5, and we're going to go from 3 to 4. All right, now I'll tell you up front, there are 2 different methods that we can use to do this one. And right now I'm focused just on this T1 to T1.5 here. We have 2 different methods. One method is that we can use the difference quotient. Because remember, the difference quotient gives us the slope of the secant line, which is basically the slope of the average velocity. That is the slope between 2 different points. So one option here is difference quotient. Not the limit in there because we're not dealing with tangent here, but just difference quotient. The other option is that we could actually just figure out what h of 1 and h of 1.5 are and then use the slope formula of delta y over delta x. Either of those two formulas will work. So of those two, yeah, this seems like the easier work here, where we just figure out what h of 1 is and h of 1.5 is, and then we find slope by doing delta y over delta x. So go ahead and do that then. Figure out what h of 1 equals, figure out what h of 1.5 equals, and then find our slope. So for h of 1, you should have found that we get 8.14 meters. Next, plug the 1.5 in. When we plug that 1.5 in, you should be getting 10.815. And now we can actually use the slope formula. So delta y, that means we do 10.815 minus the 8.14 over, now subtract the times as well. Make sure you go in the same order though. I used the second number minus the first number, so I gotta go the same order this time. That's gonna be 1.5 minus 1. You could do it in the other order, but both numbers would be in the other order, of course. Do that calculation, that will tell us our slope. So figure out that. And when you do that, you should be getting an answer here of 5.35 for our slope. Slope between those 2 points represents average velocity. And so I get a velocity of 5.35, what? Yep, meters per second. And now that you've seen the process, please repeat the process for t equals 3 to t equals 4. And when all is said and done on that calculation, you should get an average velocity of a negative 3.02 meters per second. Notice in this case it is negative, and yes, we need to respect that negative. It means that we're now traveling downward instead of traveling upward. So now our last question based on this situation is to find the velocity of the rock after 1 second. So please figure that out, seeing if you got all the pieces together. All right, and so let's make sure you're heading on the right track here. It just says find the velocity. So what does that mean we're finding? Well, it says after 1 second, so that's basically at 1 second. And so since we're looking at for the velocity at a specific time, that means instantaneous velocity. Instantaneous velocity tells you slope of the tangent line. So you're looking for a limit of the difference quotient here as h approaches 0. The derivative, in other words. When you do all the work, you should be finding here that our derivative function, h prime, is 10 minus 3.72 t. So that's the limit as h approaches 0. And now we want to know what the velocity was after 1 second, so specifically that is h prime of 1. And so we plug 1 in for t, and so that ends up being 10 minus 3.72. And so that ends up giving us 6.28. And again, include the units. And so that is meters per second.